Today we'll be discussing about naive Bayes, which is a really simple machine learning algorithm used for the purposes of classification and very often used as a simple baseline algorithm. But before talking about naive Bayes, let us talk a little bit about Bayesian networks. We've talked about Bayesian networks in different contexts throughout this course. We talked about Bayesian networks when we were talking about hidden Markov model also. But for the purposes of this trivial example, let's consider the example of rain, sprinkler, grass, wet. So these are three different nodes that you have in a graph or a network, and these nodes are random variables. The edges in this particular network are denoting direct impact. So as to say that grass can be wet if it rained, or grass can be wet if the sprinkler was on, and if there is rain you probably don't need to use the sprinkler. So there is some direct connection between rain, causality between raining and sprinkling and grass wet, and raining and grass wet. So the kind of things that we're trying to do is to calculate the probabilities of various possibilities in such networks, and specifically we look at how the joint probability of a network is computed. So in general, if you have some x1 through xn random variables and the joint probability of them is probability of x1 through xn, the formula for the joint probability is a simple formula, is the probability of a given variable given its parents. So that is, this entire thing is called the factorization of a Bayesian network. So if we go back to the previous example, we looked at the grass wet has parents sprinkler and rain, that is, they directly impact grass wet. Sprinkler has parent rain, and rain does not have any parent. So if we were to write the joint probability of this network, we would write it as probability of the variable g, grass is wet given its parent sprinkler and rain, probability of the variable sprinkler given its parents rain, and probability of rain given its parents, which are the empty set in this case. The reason why we studied this factorization is that because this factorization will be used even when we're talking about Bayesian networks, when we're even talking about naive Bayes. So naive Bayes is very often motivated with the example of spam email classification, and that's how we'll also do. Let's say we have two types of emails, either spam email or non-spam, and we denote 0 for spam and 1 for 0 for not spam and 1 for spam. And given this email, you need to have some construction of a feature vector, right? So what is the input, because it doesn't make sense to pass in the raw input. I mean, you can pass it using more advanced models, especially sequential models, but given the existing framework or the simplistic framework of creating a feature out of each input, we'll need to create a feature out of each email, feature vector out of each email. And let's consider that we first create a dictionary of words. These are, let's say, some n equal to very large number of words, and then you look at each email and then you see which of these words occur in that email. So the important step is first construct a dictionary, second look at the specific email and then put zeros for wherever that word does not occur. Let's say if A does not occur in an email, then you put a 0 here. If and does not occur in an email, you put a 0, so on and so forth. If computer occurs in that particular email, you put a 1 here. Note that we're not talking about the counts as such, we're only talking about the presence or absence. So this is just a binary case, although you could look at the counts example also. So thus each email will now correspond to a vector or feature of length n. in this case, which is a binary vector. Now, given this vector, we need to do supervised classification, supervised learning, to learn something, to learn the set of parameters which can help us predict for a new email for which we can construct this similar feature vector. So with this context, and having understood a little bit about factorization in general Bayesian networks, we'll now introduce what specifically naive Bayes does. It's a very powerful classification. I wouldn't say powerful, I would say it's a very commonly used classification model, commonly used as a baseline, not as a really strong model. And given its simplicity, it scales really well. You don't need to, it will work on very large data sets as well. And it is, as you would expected from the name naive Bayes, it is indeed Bayesian in nature. And it is also something known as a generative model. We'll not discuss about generative and discriminative models in this particular lecture. We'll do that in one of the forthcoming lectures. And thus, because of the above reasons, it's usually a really simple but good baseline. So the essential idea in naive Bayes is we are given a class y, or so this could be multiple classes. Let's say y could be either 0 or 1, spam or not spam, and you're given a feature vector. For this particular email example, now the feature vector is that huge vector of length n, where majority of the entries you would expect to be 0. It's a very sparse vector. So this is the problem setup, and this is what we're trying to model or predict, right? So given a set of input features x, you want to tell the probability of it belonging to all of the classes, and then you choose the class which has the highest probability given the set of features. The beauty behind naive Bayes is that it is as simple as just applying the Bayes rule. So we wanted to model, or we want to predict the probability of a class given features. We can just apply the Bayes rule and rewrite this expression as the probability of features given the class times the probability of class divided by the probability of features of x. So you can just verify that both of these terms equate the joint probability of features and class. The reason why we write it in this format is because in the supervised learning framework, calculating the probability of features given a class is trivial. Probability of a particular class occurrence is again trivial. Probability of features we often do not even need to even compute, because this acts as a normalization term. So this is how the Bayesian network for naive Bayes looks like. You have a class, and then you have the different features x1 through xn. So what this is in some sense telling is that once you have chosen a class, you generate these features based on that class. So each of these particular features now have a parent of class. Now this looks like the similar sprinkler, wet grass example and rain example that we've seen, but this is sort of a different structure. You see that there are edges only going from class to these of individual features, but there is no edge between these features, or there is no edge going in the other way. So then you might ask this question, that why is naive Bayes called naive? Like, what is so naive about it? The naive thing about naive Bayes is that if you were to look at this particular graphical model of just Bayesian network, you could easily write the factorization as follows. The probability of x1, all the variables given y, or in fact you could just do the joint probability and divide by the normalization constant probability of y over here. So either way, you can write this in terms of probability of x1 given its parents, which is just the class y, probability of x2 given the parent class y, so on and so forth. So can you think for a minute that what is so naive about this particular assumption, or this particular factorization, or this particular structure that we have imposed on this graphical model. And the naive assumption is that we have assumed that x1 and x2 are independent of each other given the class y. So which is to say that if you were to write the probability of a feature x2 given x1 and y, it is going to be equal to the probability of x2 given y, since x2 and x1 have nothing in common, so they're completely independent of each other. Now pause for a moment, think about the validity of this assumption. So let's say you're given a class spam, and this will have various words. So think about the different words you would identify with a spam email. It would be price, money, important, lucky, so on and so forth. Are all of these words really independent? Probably not. The occurrence of one such word is highly linked to also indicate the occurrence of similar such words. So thus the naive assumption is going to break in many real world scenarios, but still we can use it for under the same simple model assumptions. So what we need to predict in naive Bayes is, this is revisiting what we had seen earlier, is the probability of y given the feature vector x, which we can rewrite as, using the Bayes update rule, as the probability of the features given the class times the probability of the class itself divided by the probability of the example, or just the evidence. Now we've already seen that how we can factorize this particular expression. So if we can go back, then the probability of x1 through xn, which is the feature given y, is individually broken down into x1 given y, x2 given y, so on and so forth. So that's why this particular expression is really trivial to compute. And we look at a couple of examples to solidify our understanding in this particular matter. So if we come to the spam email classification problem, we now first know that y can be either 0 or 1, where y equal to 1 indicates a spam email and y equal to 0 indicates a not spam. And each of the individual xi's, so we created a vector of binary vector of length n. The trivial way of computing, or the whole beauty of naive Bayes is that it just boils down to such simple calculations. So if we go back, this is what we want to compute, right? Given an example, given a new example or unseen example x1 through xn, we want to predict its class label y on the supervised, in the supervised settings for the same examples. And this particular expression can be further broken down as this. So you need to, in the using the supervised setting, you need to compute or learn these particular probabilities. What is the probability of x1 given y? And we know that each of the xi's will be either 0 or 1 in this case. So probability of xi equal to 1 and probability of xi equal to 0 given y equal to 1 is what we are trying to compute, which boils down to as simple as the count of xi equal to 1 and y equal to 1 divided by the count of y equal to 1. So that's just conditional probability definition. Similarly, you can compute the probability of xi equal to 0 given y equal to 1. So once you've computed all of these quantities, and then you can also compute probability of y equal to 1 and probability of y equal to 0, they would should sum to 1. Once you've computed all these numbers, it's as simple as just plugging in these values and being able to make predictions. So that's why if you see that this model is going to scale really well, it's a really trivial model and the parameters are trivial to learn. And the prediction is also simple to make. It is just going to involve multiplication of some such numbers. Yes, so we also discussed that probability of y equal to 1 is simply the count of y equal to 1. So number of times y equal to 1 occurs in the train set divided by the total number of samples, and similarly probability of y equal to 0 is the number of times y equal to 0 occurs in the dataset divided by the total number of samples in the trained dataset. Let's work out one full example to understand even better. Let's consider this example in which the size of the vector which we were talking about is only 3. So you have only 3 words, let's say a and the, and you also have these labels y equal to 1 or 0 indicating spam or not spam. So given these 10 examples, we want to now learn a naive Bayes model and then predict for a new example. So a new example means a new tuple of w1, w2, w3. So at this point I'll request you to pause the video for 3-4 minutes till you're able to work this entire thing on your own. So you want to be computing the probabilities of w1 equal to 0 given y equal to 1, w1 equal to 1 given y equal to 1, so on and so forth. So there are 4 quantities you require for w1, 4 for w2, 4 for w3. Although technically you don't require to compute all 4 given the sum rule of probabilities that you can simply use, and then you can easily compute probability of y equal to 1 and y equal to 0. Assuming you stopped the video and you worked this example out, let's take the case of y equal to 0. So we have index 2, 4, 6, 8 and 9. So firstly you have 1, 2, 3, 4, 5 cases of y equal to 0 and 5 cases of y equal to 1. So probability of y equal to 0 is 0.5 and the probability of y equal to 1 is also 0.5. Now let's consider the case, let's see which we have taken. So we have taken the case of y equal to 0. So y equal to 0, then let's just concentrate on the w1 column. So we have y equal to 0, w1 equal to 1, y equal to 0, w1 equal to, y equal to 0, w1 equal to 0, y equal to 0, w1 equal to 1, y equal to 0, w1 equal to 1, y equal to 0, w1 equal to 1, and y equal to 0, w1 equal to 1. So we have, out of the 5 examples in which w equal to 0, y equal to 0, we have 3 examples where w1 equal to 1 and 2 examples where w1 equal to 0, right? So probability of w1 equal to 0 given y equal to 1 is 2 over 5, and probability of w1 equal to 1 given y equal to 0 is 3 over 5. Did I say something wrong? Y equal to 0 has 1 0 and 2 0 and 1 1 2 1 3 1. Yeah, so w1 is equal to 0 should have been 2 or 5, I guess. Yeah, these two quantities have somehow been swapped wrongly in this example. Similarly, you can compute the probability of w2 equal to 0 or 1 based on y equal to 0 or 1. Similarly, w3 equal to 0 or 1 based on y equal to 0 or 1. Once you've computed all of those quantities, then let's say you're given a test email 001, which you need to classify using naive Bayes. So all you now need to do is to just plug in the Bayes rule formula and just do the computation. So we have probability of y equal to 1. So we compute both the probability of y equal to 1 and probability of y equal to 0, and then we compare which of them is higher. Whichever is higher is the assigned probability to this test sample. We have w1 equal to 0, w2 equal to 0 and w3 equal to 1. So using using the Bayes update rule, this expression can be written as probability of w1 equal to 0 given y equal to 1, w2 equal to 0 given y equal to 1, w3 equal to 1 given y equal to 1 times the probability of y equal to 1 divided by the probability of this observation. We will just denote that with z. So you can compute this entire number, which will turn out to be something, and you can similarly compute the probability of y equal to 0 given this test sample which is, let's say, 0.6 into 0.4 into 0.6 into 0.5. And if you take the ratios of probability of y equal to 1 given the example and probability of y equal to 0 given the features, it will turn out to be 2. So this is a simple neat trick that you don't even need to compute the normalization constant. And given that the probability of y equal to 1 is greater than 1, thus this example is classified as a spam example. So naive Bayes, when we're using for email and sentiment analysis, there is a small caveat. Let's try now use it for sentiment analysis, where let's say the sentence is that this product is pathetic. We would have assumed that the sentiment associated with this sentence is negative, given that you're talking about the word, using the word pathetic. And here naive Bayes would simply amount to storing the probabilities of words belonging to positive or negative sentiment. For example, pathetic would have a largely negative sentiment, good will have a largely positive sentiment, so on and so forth. So each of the word gets assigned some probability of belonging to a particular class or being generated from a particular class. But if a sentence given to you is something like that, this product is not bad, this would be hard for many modern sentiment analysis tools, but naive Bayes you wouldn't expect it to do really good, because an important aspect that this is missing is the sequential aspect of the data. So it treats all the words as first independent, all the features are independent, and then it also foregoes any relationship or any ordering that occurs between the words. Like not and bad occurring together have a different meaning than, let's say, not separated by a few words and then bad occurring. But of course, you get some disadvantages and some advantages. In terms of advantages, you already saw that you get a lot of speed, you get something really scalable model and something which is really easy and interpretable. But in terms of the disadvantage, whenever the assumptions start failing, the model will start performing really badly. We can use naive Bayes for the continuous data example also. We have thus far seen it when the data was, or when the example was for when the input features were discrete. But now we're talking about Gaussian Naive Bayes when we assume that the input data is on a continuous scale. To understand this Gaussian Naive Bayes better, let's try and first create an example for ourselves and then try and work out through the math. So we say that let's say that our problem that we want to solve is classifying a person based on their height in feet or whatever units you want to use, and we just created our own data set just to sort of help us understand this concept better. We said that the height of the males is normally distributed with a mean of 6.1 and a variance of 0.6, and the height of female is normally distributed with a mean of 5.3 and a variance of 0.9. So larger variance, that's why you see more spread, and you can already see some things from this particular plot. So this is a plot where I actually sampled, I believe, 1,000 samples each from these two distributions, and then I did a kernel density estimation plot, KDE plot. You can also visualize the same thing using something known as a Weiland plot, so which also helps you to sort of understand this entire thing better. So for example, in this you're also getting a box plot, and you also see that firstly in the females you see that the spread is more, and that's largely because we had created the data set in this fashion. And you of course see that the median height of a female is lesser than the median height of a male. That's just as per this simplistic data set that we have created. So coming back to the density plots, so think of them as a more refined version of the histograms that you've been accustomed to drawing. So natural question that you will want to answer is that given a new person and their height, let's say 5.5, would you classify them as a female or male? So let's go back to this, somewhere around 5.5. So would you classify them to be a female or male? So you'd probably classify them to be female, given that the height of the female is a normal distribution about mean 5.3, whereas for the male it is a normal distribution about 6.1. So 5.5 is much closer to 5.3 than 6.1. Thus you would expect it to be a female. You can do the same thing in maths. So you compute the probability of female given the height is 5.5. That will turn out to be 0.43. So all of these are based on these two distributions that we have, right? And the probability of male given the height 5.5 is 0.22. Clearly the probability of female given 5.5 is more. Thus you would classify a person of height 5.5 to be female according to this trivial example that we have taken. And you can very easily see that. So we have drawn a line at x equal to 5.5 and see where it cuts these two density plots. It cuts the density plot for male at around 0.22, which is the same number as here, and for the female as at 0.43. Naturally you would there is more probability of this example belonging to a female class. So let's rewind this discussion a bit and let's see how we would have solved this problem in a machine learning sense. So I already created some distributions and gave it to you. So in a machine learning sense, in a supervised learning sense, you would be given samples, these 1,000 samples of, let's say, males and females, and so their respective heights basically. So y equal to 0 or 1 depending on whether it's a male or female, and the heights of 1,000 samples of each. So you're given this data set of 2,000 samples with the output label 0 or 1. Now for each class, let's say class equal to male, you'll say that it's distributed normally, and you learn the parameters for this normal distribution. You could just use simple maximum likelihood estimate to learn the parameters. And so maximum likelihood estimates would, in fact, if you can recall, for such cases be the sample mean and the sample variance. And similarly for the class equal to female, you again calculate the sample mean and the sample variance, and then you've basically obtained these quantities. Now once you've obtained these quantities, you can simply plug in the formula for the PDF of a normal distribution. So that's how I've computed these quantities. So this is probability. You look at the probability of 5.5 being generated from this particular normal distribution and from this particular normal distribution, and then you just compare which of them is more likely. So that's how Gaussian Naive Bayes works. This was an example in 1D, but I'll now take an example in 2D to help us appreciate the notion of naiveness and naive Bayes even better. So in general, we can have C1 through Ck classes, and we have continuous attributes. For a single attribute x, for class K, we can calculate its mean and variance, as I discussed. That's the same as the MLE estimate. So this is at the train time, and at the predict time for some observation V, we can calculate the probability of okay, so we want to calculate the probability of the class given the sample. So this is, you wanted to calculate that what is the, I see, okay. So you calculate using, for each of the class means that for class C1, which is C1 is, let's say, this particular normal distribution, you have the mean and the variance, Given a sample, you can calculate the PDF, and for class C2 you can again calculate the PDF given this particular class. You can compute these numbers, right? But this is not the end of the entire calculation. There are some other terms also, as in there is terms for probability of individual classes also. So the final output, which is the posterior update according to the Bayes rule, is probability of class given the sample, which would be obtained by this term multiplied by probability of class Ck divided by the normalization constant, right? So that's how you will predict for a test case. And now let's come to a 2D example. Let's assume that the two features of interest are a person's height and their weight, and based on this, now we want to classify them as female or male. So would you expect a person of height 5.5 to be a female and weight 80 to be a female or male? Again, let's assume that we got some data set. In our case, we generated that data set ourselves, and what I've done here is I've taken that data of heights and weights. The blue set of points are for the females and the red set of points are for the males, and then I've drawn some contours. So these contours are basically telling us these contours are basically in the two-dimensional space. You're plotting the PDFs, right, which would have been normally a surface plot. Since the data is 2D, the surface plot in 3D would give you a PDF of this data, but I'm here just showing it via the contour plot. Basically, this is saying that a lot of the probability mass will be concentrated here, lesser probability mass is concentrated in the outer circle, and so on and so forth. Now if you look at these particular contoured lines, you'd see that there is absolutely no element going in the diagonal directions, either of the diagonal direction, and they are perfectly aligned with the axis. This is because naive Bayes says that the features are independent. So knowing about one does not tell you anything about the other given the class label, which also now tells you that in a multivariate Gaussian, when you're trying to fit naive Bayes, you have to assume or you make the covariance matrix as zeros everywhere except the diagonal. So it's just and the diagonal elements can be different. So in this particular case, we see that there is more variance in one particular direction compared to the other, right? So that is fine, but there is no cross correlation or cross covariance terms, so as to say. Now, given this particular example of height 5.5 and weight 80, so you see height 5.5, weight 80, you'll see whether it's more likely to be a male or more likely to be a female. So in this trivial example, it is very likely to be a male because you have more probability mass. You probably have more probability mass around here than for this particular contour over here. Finally, let's take now a fully worked out example. Not really fully worked out, but it's an example borrowed from the Wikipedia article on naive Bayes, and you can refer to that article to fully work it out and compare your calculations. So you're given three attributes now: height, weight, and foot size, and two classes, which is the gender. So again, we do the simple things, as in for each of the feature, we see for each of the class its variance and its mean, right? So you look at the male class, you look at the heights. What is the mean of their heights and what is the variance of their heights? You look at the females, what is the mean of their height and what is the variance of their heights? You look at the weight attribute. For males, what is the mean weight and standard deviation of the weight, so on and so forth. So you do this for all the features across all of the classes, and you'll tabulate a table which looks something like the following. You calculate the mean variance for each of the variables or each of the features for both the classes, and Now given a question that the height of a person is 6 feet, the weight is 130 pounds, and the feet is, or the foot size is 8 units, classify this example as female or male. Now without doing anything, we can just look at this particular table, and we said that the weight is 130 pounds. Weight is 130 pounds is way closer to females than it is for males, but the height is 6 feet, which is closer to male than female, but still not, the difference is not as stark as in the case of the mean weight. And the feet is 8 units, which is again probably closer to the female data in this particular data set. So just by looking at this, you would expect it to be classified as female, but then there is this full Bayesian calculation that you can do. So the simple idea is, again, you want to calculate the probability of this particular sample being from a female whose height is 6 feet, of this person height of 6 feet, 130 pounds and 8 units. You factorize this, or you just apply Bayes rule to write this as the probability of 6 feet given female, probability of 130 pounds given female, probability of 8 units given female, and probability of female, which is half, since half of your samples are female and half of your samples are male, divided by the probability of the observation itself, which we can just treat as a normalization constant. So let's look at one particular term here, probability of 130 pounds given female. So probability of 130 pounds given female is, you're trying to see from this particular two set of rows, right? So you have a normal distribution with mean 132.5 and variance 550. You're trying to see what is the probability of an observation 130 from this particular normal distribution, which is just 1 by root 2 pi sigma squared times exponentiation of minus the mean minus x, which is the target or this test samples x squared divided by 2 sigma squared, which will turn out to be 0.0167. Similarly, you can do the computation for all of these quantities, right? And then finally, when you solve this, you'll see that the probability of female given the data is greater than the probability of the class being male given the data, and thus you'd predict the sample to be female. So before we stop this lecture, a really simple but important caveat is that one particular thing you need to be very careful about naive Bayes is that you're multiplying a lot of numbers. So this is really trivial, but if you have a large feature set, you will be multiplying a lot of numbers which are probability numbers, so between 0 and 1s, and then there is a really important, very non-trivial chance that you'll hit numerical underflow. To avoid the same, you can use the trick of solving this or dealing with these numbers in the logarithmic space, and then again converting back to the exponential space if needed. But otherwise, at the end of the day, what you need to do is to compute the probability of class 1 given the input features, class 2 given the input features, so on and so forth. Then you just need to see which of them is the highest. You don't never need to compute the normalization constant for this trivial problem, since you can just see for all of the different classes the probabilities should sum up to 1.